The topic for today is leveraging OpenAMP in embedded mixed safety critical systems. So we have seen a lot of heterogeneous, homogeneous systems or cores coming into the embedded system in recent times. We'll now focus only on how OpenAMP can be used in mixed safety critical systems. But before that, I'll give you a brief overview of where are the trends and what is happening in this space today. So firstly, I think you're all aware what is multicore and why is it becoming so much popular. The main reason for multicore is it enables data and task parallelism. It is mostly dependent on, it is moving away from sequential programming to how we can use program or parallel programs parts and assigning them to processor cores. Because if you have two cores, it's advantageous to use for improving the performance. So for that, a different way of writing a code will also come into picture. But today we'll only look at how cores or how we can design systems and what softwares can we use or frameworks can we use to take advantage of this multiple process available to us. Okay, or multiple cores, I'll put it like that. So in the beginning, if you see at the initial, at the start, there were only single core systems. Then it moved to multi-core CPUs. Multi-core CPUs then are now moving towards, or already are there so many in your HPC systems, but high performance computers. But not only on that, due to the AI ML advancements, it's also available on embedded devices, on edge computing devices. If you use the, if you look at the architecture, they have CPU and GPU. GPU is targeted to accelerate only the AI calculations, and CPU does the general functionality of the instructions, whatever is given. So this is the way the trend is moving. So heterogeneous computing is where their cores are not identical. So if you look at ARM Cortex R5, there are two cores in it. Both the cores are identical. So what I mean by heterogeneous is, look at Xilinx. I'll give some examples. In that you will see there is ARM Cortex R5 plus ARM Cortex A7. A7 has 4 cores, R5 has 2 cores. Now a package SoC of this can be a heterogeneous system, can be looked at it. So how do you communicate between these two heterogeneous cores within each other for many purposes, which I will explain in the next coming slides. So important thing to remember here is, this is all asymmetric processing that is happening. That is, each core is responsible for operating independently, performing their own dedicated tasks. It's not the same task that they are doing. So a simple example you can keep in mind is a CPU and a GPU. A CPU will follow a general set of instructions, whereas GPU can be given some part of the code where it can perform accelerated computing or calculation that is required. So the way to do that would be a lot more in the coding or the way you program a system. Like for example, in NVIDIA, there is a CUDA framework where they use to compute such things. So that is a brief overview of where the industry is going and what we are seeing and why this becomes important. So a little more if you look at multi-core systems. Why do we need multi-core systems? The main reason is the boot sequence. If I start one core at some time and I start another core at a different time, the order or the computation or the way I'm sending from one core the data to another core becomes important for it to compute. So we'll have to have the boot order or the sequence correct. Then there should be intercore communication for sending the data across for a powerful core to be used. So these could be one of the important reasons for AMP systems or multi-core systems. But what are the challenges? So there are so many challenges that you can see. They would think about, what about security safety issue? What about if one core fails, how do we communicate back to another core? What could be the debugging methodology? Because I don't know which core has failed, which core is good, right? So it becomes important to understand there are certain challenges, but there are challenges so we can overcome them by using either a hypervisor or a multi-core framework. I'm today only focusing on multi-core framework, the second part. But I'll briefly explain to you what are both of them. A hypervisor is a complex software component which resides in all the cores. It is a component that will reside in all the cores. And what it does, it actually virtualizes the operating system, or it provides the shared resources. So it is a manager that manages the resources between the cores. So it is very important to note, hypervisor is very good for homogeneous systems, but not for heterogeneous cores. So what happens to heterogeneous cores? Heterogeneous cores can use now multi-core framework, which OpenAMP is a part of multi-core framework. What happens in a multi-core framework? It is a software component enabling for AMP systems which resides in each core. So there will be a software component residing in one core. There is a software component that is going to reside in another core, but both are OpenAMP. We configure them as either to be master or either to be slave, so that the communication between them happens. So we will look now into detail of multi-core framework. So in multi-core framework, the most popular component that is available, or the standard that is available as a standardized for AMP system, is OpenAMP. It is open source too. It is a framework used for communication between heterogeneous cores itself. It is for AMP systems. So what is OpenAMP? Asymmetric multiprocessing system. OpenAMP it is. So what is its object? So as challenges that we saw in the earlier slide of OpenAMP, the main important objective is to simplify the heterogeneous functionality, to control the boot order, to ensure the interprocessor communication happens. It manages the lifecycle environment. It helps to share resources between the environments. So any OS porting will automatically, it is very easy to port the OpenAMP because it acts as a separate component. So it can be cross-compiled and put into any OS or operating system. So it works in multiple configurations. It can be used in bare metal. It can be used on Linux. It can be used on, say, some embedded OS. So it can be used across various operating systems. So it is not only for a particular operating system. So we'll look at it, how OpenAMP's internal structure looks at, give you a brief overview so that you can just go ahead, download and start doing this. So there are members of OpenAMP. Mainly the players like ARM, NXP, NVIDIA, Xilinx, ST, all these people are there. And so there are also Mentro Graphics, which Linux related, the things that have OpenAMP, they are contributing to the community. So there are many people like Linaro, all those things. So the relevance to the industry. So let's say now look at it from a different angle. So now we saw the technology, why it is important. Now look at the business use case or the application where it will be used. So if you look at any industry for that matter, you can use it in any semiconductor application. You could use it in automotive, in a digital cockpit, because digital cockpits today use hypervisors also. And the safety is a very big importance there, because it has to be certified. And in industries also, IEC 6150 standards are there, where if you have to ensure that the entire system is redundant and it should be safe. So in these kind of safety critical design applications, OpenAMP becomes a very important, because the component can be separated out. The design can be done in such a way that it can be part of the non-safe critical area, and the critical area can only be certified. So we will see how we distinguish between these two things. But in an industry approach, you can see that it can be used in anywhere you are looking at a heterogeneous course. You're looking at safety critical applications, and you're looking at reducing your power consumption with a hybrid design approach. OpenAMP becomes much of importance. So when you are analyzing whether to choose from an hypervisor or an OpenAMP framework, give a thought of, can I tomorrow will it help me for heterogeneous systems? Will it help me to manage resources better with an OpenAMP framework? So you can look at that way and analyze whether hypervisor suits your design, or you can go with OpenAMP. Okay, let's now look at the key components. So now we'll go in detail of OpenAMP. So where does OpenAMP sit actually? Like I said, there will be a hardware layer. Then on top of that, there'll be an OS. So OpenAMP can sit in the application layer of the OS. Like it can be in part of the OS itself. Like when you compile a kernel, you can compile it and add as a package, OpenAMP package in the Linux kernel. So it is more of a middleware, you can call it as. So it has a device driver for itself for communicating between the process. That is a remote proc and as RP message. So these two important factors you have to keep in mind. The important thing is there are two components for OpenAMP. One is remote proc, another one is RP message. What is remote proc? Remote proc is an important component because it helps to even load the operating system of the other core. So if you have two cores and you can provide the image to the master core and you can set the boot sequence when it can load the image or that particular image to the remote core, and it can also control the turn off and turn on of the core. So imagine a place where one of the cores fails or some application is stuck. The master has the capability to reset the other board also, reset the other core, I mean, in this case. So it can start the system, it can stop, it can reboot, it can reset, it can release, it can shut down. So all the functionality or the control, you can say, of what you can do for a remote core, it does all those. That's the component of remote proc. Then there is RP message. So this component is basically an used for API, for inter-processor communication between the two cores. So I want to pass a message. I do certain, like imagine a system where there is a visual display and where there are sensors connected. Now the data from the sensors that are coming in, you want to show that display on. So you can divide the cores in such a way. One is the application processing unit and one is the real-time processing unit. The real-time processing unit can take the data, read the data from the sensors, compute it, and can push it to the application processing unit using RP message. Application processing unit can display it on a LCD screen or whatever is your configuration of the system. So you can look at it and imagine it in that way. How can I make use of this heterogeneous core systems in an effective manner? Using these two becomes very important, and this is part of the OpenAMP. So I'm a little bit diving deep into the OpenAMP software code actually. So you'll get to know there is remote proc, there is RP message. Then there are certain APIs that are already defined. So these APIs you can make use of and design your system. So there are different configurations for OpenAMP also. What are the configurations? So one is, like I said, OpenAMP can be done on either it can be on a bare metal, it can be on an RTOS, right? Or it can be on a Linux, of course. So there are different combinations and different places where you can put this OpenAMP framework also. It could be placed in the user space, it could be placed in the kernel, it could be placed in part of the hypervisor system also. We'll not get into that detail, but hypervisors also use OpenAMP today, can be used in part of a OpenAMP. I'll just show you a little bit, but I think important to know is these three configurations. One, master is the Linux, and the remote system is an RTOS or a bare metal. So you can see in the picture that they are communicating. There is a remote proc or RP message component, which is nothing but together known as an OpenAMP framework. And there is an OpenAMP framework here also as not part of the RTOS or the bare metal. It is resides as a different component itself. It's not integrated to the RTOS, and they communicate using this. When I say in part of the Linux, I mean it can be configured or it can be a loadable module. It can be converted at a device driver level and loaded, or it can be part of an application. So that's how we have configured here in the Linux. Then there is a second configuration where the master can be an RTOS and the remote can be Linux. So in that way, the RTOS wants to have the control, and the Linux will be the remote device here. Then the third configuration is where the master is the bare metal and slave is also a bare metal or an RTOS system. So like I said, it is not compulsory that there should be an OS for OpenAMP framework. It's just a configurable framework module where you can use the APIs and communicate between master and remote systems. I hope this is clear. I'll move on to the next. Then there is this multi-core framework architecture. So we are now going to come in detail understanding how this OpenAMP can be focused only on right now on mixed safety critical applications in this context. So it can be used in various. I have taken the architecture of how we can use OpenAMP, how it fits into the mixed safety critical applications, because mixed safety critical applications are of importance because of the reason of the complexity of the safety that is involved in those applications. Okay, so there is different kinds of architecture. You can look at it as an unsupervised AMP architecture. So in an unsupervised, what happens is, look at the picture on the right side. There is a bare metal where there is an multi-core framework, and there is an RTOS, and there is an Mentor embedded Linux RTOS system. Look at Cortex M5 is running this M5 core, and there are A53, there are 4 cores. It is running using this Linux. All 4 cores have being used. It is running the embedded Linux. Okay. So now, what is unsupervised? Unsupervised means the participating. What happens is there is not a requirement of a strong separation between the participating operating systems context. So participating operating system meaning bare metal and RTOS. There is not required of a strong separation. Strong separation means when it is, you should have another layer where it will be supervised. So we will check the supervised architecture in detail. So here to explain it, you can look at this way as one RTOS doesn't have the control over another. Control in the sense it does not have require separation. So you can use some part of this code here. There is no segregation or separation. So to explain this in simple way, you can think of it as a system where you are running in your normal context, not in a safety context where there is no strong separation between the RTOSs. When separation happens, then there is a way of protocol to communicate between each of the operating systems. So here Multicore provides simple and effective way to using a master software context on a master processor, and can manage, I told you, using the remote proc, you can manage the life cycle of the remote core, as well as offload computation and other computing related details, resources into the SOC that is typical in unsupervised architecture. Like you can, your calculation intensive code can be moved to another core or process. Now, there is next known as supervised asymmetric multiprocessing. Yeah, in this supervised, what happens is that it requires isolation, complete isolation between the software context, and virtualization of system resources happen. That means if I have a memory using hypervisor, it controls the memory in the context of how it will use in that entire core level. So in that way, we have to use a hypervisor. I told you that OpenAMP, we can integrate part of the hypervisor system also. So this is how it happens. There is a hypervisor system where you can integrate the OpenAMP inside it. Then what happens is there is a supervision happens, because hypervisor will note all the virtualization related things and all the shared memory concepts of memory allocation, and it supervises that, and it provides the virtualization services. The hypervisor, I'm going into a little bit detail here. So it will virtualize the operating systems, and it will give a component of, there will be a remote proc RP message because there is a multi-core framework here, and it will provide for the Linux guest 1 also. So you can look at the picture to get a better idea. Then there is an RTOS and a bare metal. So the control is not through the MEMF. You have to remember that. Now, because of the supervision, the control is through the hypervisor. The hypervisor can control the RTOS as well as the bare metal to share the resources between its own course as well as the other course in context. So this is the, you can download the Xilinx MP SOC software manual and hardware manual and look at it, how they have structured. It is one single SoC chip. Now, how to make use of all these cores is part of your architecture or design that you do. And the best way to do it would be to use the multi-core framework, because it gives you an advantage of using it for heterogeneous cores. And one important thing is you can start off working on any code using an unsupervised architecture. Supervisation will require for applications where there is safety, where there is like a digital cockpit, when we have to control the resources, when there is resource constraint. But a simple bare metal, if you want to start off using OpenAMP, I would suggest just download. It is available freely using the Xilinx platform or any other, even your system, because it can work on Linux system or any bare metal. Cross-compile it, put it to your bare metal devices or a device. Take it as a 2-core only, to a single. You will have homogeneous only you can start with, not require heterogeneous. Then you can move ahead for heterogeneous, but you can use a homogeneous and start off working on it. So we'll move to the next thing. So application, like I was saying, so different configurations I thought I can just put in to give you a relation of where it can be used. So the first is where we saw the configuration 1, where the master is Linux and the slave is RTOS or a bare metal. So this architecture is used in data intensive applications, where the focus is on display interface and mostly in non-critical subsystems. Like I said, if you look at this kind of architecture, you will see that the Linux, the bare metal is talking to sensors and getting the data, whereas a Linux component can be integrated to any kind of a data intensive, in the sense it can be visual device or display device, a simple display, can use that and do it. So in this way, this configuration will work. The next configuration, if you look at it, could be in medical critical applications, a little more critical, where the RTOS becomes the master and the Linux is the slave. It can be worked as a platform where they will have an application processing unit and a remote processing unit. The RPU can be run on a safety certified. So the RPU, that means the real-time processing unit, you can separate it out because the core is different and can be safety certified. So in that way, we can use it in a medical context. Then the last, where there are 2 bare metals, that can be used in any industry application where you measure the pH measurement systems, or you can use it in any simple applications where you are just triggering an alarm based on certain conditions, or compressor units, just creating a sensor module there or a device there. You can use in any industrial applications over there. So these are the 3 different configurations where you can use. It is just that when you're designing, you can have these sample architectures in mind, so that it becomes easy for designing systems. It's not that you can't use RTOS in some other thing, but it is like the design will not meet the importance, because if you use RTOS for safety critical, then you will have to do a little more data of separating and even ensuring that the entire code is run through safety. So it's not preferable, but it's not that you can't do. You can go ahead, but it may not meet the needs of the design of what system you are designing for. Okay, so we will now look at how the boot up, and then we look at RP message also a little bit, how the boot up of remote proc happens, how the control is given to the remote, from the master to the remote. So the master first calls, so these are the APIs that are there in the manual itself. So I'm not going to go into detail of what these APIs are, just written a high level of how the control shifts from a master to the remote system. So if you look at the master as application calls like remote proc init API, then it will decode the firmware, excuse me, decode the firmware, that is the ELF image, and obtain it from the resource team. It will carve out the memory. So what it is basically doing is, why is it decoding the firmware of ELF and obtaining the resource table? Because it wants to know where the remote firmware lies, how to load the data or the image into the RTOS if it wants to, or where that the remote core does it lie, so that it gets the control. Then it also has to know the memory, carve out the memory. It creates RP message and RP proc. So there is another important thing known as virtual IO device, which is part of OpenAMP. So I have not covered that because I wanted to first give an overview of what is remote proc and RP message and the context of this entire discussion was how we can use it part of the safety system. So virtual IO is part of OpenAMP itself. It's a little more complex in terms of how it creates IO devices, virtual IO devices, so that the two cores can share it, also can use or make use of it, or how the master can change the data in the remote also. So I'm not gone into detail, but you can definitely go through and have a look. And if there are any questions, you can get back to me. So after this, coming to this, once the VirtIO device on the master for communication on with remote, so they has to set up a channel, right, to communicate between the master and the remote. That the VirtIO device does to communicate using RPA message API calls. It will communicate, but it has to create a virtual channel to communicate. So that's what this VirtIO does. Then the application calls remote proc boot API. What does remote proc boot is? It starts booting or loading the firmware for the remote data. So it's load the text and data for remote firmware. Then it has the control start remote processor, which is again remote proc underscore start remote. That is a API that is there. You can start the remote processor. Once the remote processor starts, it takes the so it can be a bare metal or an RTOS. Application will call this remote proc resource API, resource init. So resource init has the data that you had put in by reading the text and firmware data and load. So it will do that. Then it will create the memory mapping based on the resource table that you had updated, and obtain the resource table and you are updated based on your reading. That basements on the master's reading, it will be creating memory mapping based on it. Then it will create RPA message VirtIO, and again it is a channel for communicating between the master itself. Then it will advertise remote channels to master. So it will tell, this is my channel. So master has created a VirtIO device channel. Remote proc will send, this is my channel number, channel it will advertise. Then master will know this is the core for this, and it will know the mapping also, because it will send that also as the advertisement once the communication is established, and then it will map it also accordingly. So it knows when to communicate to the remote. I hope this is clear. We'll move to the next one. So example architecture for mixed safety critical systems in patient monitoring. So let us take with an example. So there is a real-time processing unit and there is an application processing unit. The real-time processing unit is nothing but it has a safety critical certified RTOS. Okay, it is the one that is managing or maintaining the real critical components of the system. It has a safe app as well as it has an OpenAMP framework. Now this is also, if you look, you can see that there is a difference. It is a different component. Why we have done this is for safety critical system. So what you understand by safety critical is a system where there is a redundant system as well as a normal working system. How it is being designed is that the safety of the system is given the highest importance. There are many levels to it, SIL levels. But one thing to realize here is, for any condition, if a failure happens, or if a kind of a risk happens or hazard happens, the system always moves to the most fail-safe condition. Fail-safe in the sense it moves to it closes the valves if it is open. It goes to it only shuts down all the other features. It only goes to a safe system where you have a redundant system working on a simple thing. So it goes to the fail-safe mode is what we say. It also means that there'll be multiple cores, because if you look at your aircraft design also, which is a very higher order safety, I'll not go into the details, but just look at it. If one of the engine fails, you always have the other engine as a backup, and they have designed it in that way. So in embedded system, if you look at it, if there is one processor that fails, you have another processor which will at least not make it unsafe. It will ensure that it closes the valve. It does all that. It has control for all of those things. So each critical component will have a redundant system in place. So that is a safety system actually. So how we are going to use this? So there will be an OpenAMP framework which can act as a communication between the remote and the application. So application processing unit is non-critical, and this is critical. Why we are doing in this way? Why you can, without this or simple OpenAMP, we can communicate? Yes, you can. But the important factor here to note, remember is this OpenAMP framework is residing in the safe part of the code. And this is in the non-safe part. So we have to ensure that the OpenAMP framework doesn't impact the other safe related aspects of the code, because one thing is the segregation, because in safety system design, they will say that if anything you add, how are you making sure that it will not affect the safe app or the safety features of it? It is not by simple mentioning of it. It is by testing. It is ensuring that the component is different and independently certified that it will not cause any memory leakage, it will not do anything. So that there are many aspects of it, of designing a software safety unit. I'm just telling you in brief and in a simple way that it should ensure that it does not interact with the safe app. And it should ensure that the messages that are sent are secure, not only in terms of CRC, but ensuring that the channel is safe, so that there is no noise or something else cannot change the data in those aspects. So in that aspect, OpenAMP becomes important because it can be determined, it can be certified separately. So these are the ways in which you can, design the whole mixed safety system also. So next is, there are some now moving towards what is happening and going to happen in future, like that. If you see, there are many ways of designing these things. One is a hybrid design approach. In hybrid design approach, what happens is there is a hypervisor also will come into picture. So if you can see, this part is the safety certified and this is the non-safety certified, non-certified. So this is a zone of trust. So this zone of trust is going to be tested intensively, ensuring that the non-safety part does not change the data in the safety part. That is the thing. So here you can look at it as it can be used in instrument cluster, HVAC, telematics, V2X, all those things. And this is in infotainment, etc. So here you can see that there is a certified RTOS, that is embedded Linux. So there is hypervisor because it is a kind of a supervised architecture that we are moving towards. So it will supervise all the different kinds of memory, shared resources. It will run the guest operating system. It will create, it will destroy. It is managing the entire safety component, but it is giving an OpenAMP. Why it is used is to communicate, so that in the zone of trust, this feature of OpenAMP ensures that between the cores, there is no harm that is going to be caused. So that is the way that the safety critical design, or a robust and effective manner of a design, can be created. This is going to be also, if you look at it, is very going to be cost effective. Because in a traditional safety design, you used to use two controllers, two cores, two controllers. Now you have multi-core systems. You can make use of that and create redundancy within the course itself to make use and help you in the safety design approach. You don't have to design a separate same board, same redundant system on the same board in a different way, and you will save the bill of material cost also. So in that way, this OpenAMP can be advantage for heterogeneous cores also. So the cores are going to be different, so it will help a lot. Okay. So there is a demo also on OpenAMP. Next steps on the demo, you can go through that. It is very helpful. You can check in my paper also. It will be there, how we have done and what are the details of all these related things. Then there is a OpenAMP community also, where you can go and download from the GitHub. So this is a GitHub community. You can go ahead, download this, start working on your Linux systems itself. So we released a patch where we can, talk in the Linux itself. So in the Linux itself, in your laptop, you can have it on a different cores. You can enable it, and how we can communicate between one core to another core is also shown. You can go have a look at it. Yeah, that's all from my side.